Swayam Prabha. Digital India. Educated India.
Remediation of dyes in textile effluent, current treatment technologies with a proposed alternative. Lecture number 29. Slowly we are coming to an end of this lecture series and we have reached lecture number 29. Remediation of dyes in textile effluent, current treatment technologies with the proposed alternatives are that textile effluent containing dyes poses significant environmental challenges due to its high toxicity and potential for water pollution, and this we have understood in the last 28 lectures by now. Several treatment technologies have been developed to remediate dye containing effluents, each with its own advantages and limitations. Here are some current treatment technologies along with the proposed alternative. So, what are the best alternatives for remediation of dye? Because that seems to be the most important and biggest culprit in the textile effluent, at least apparently. Biological treatment, biological processes such as activated sludge, aerobic and anaerobic digestion and phytoremediation utilize microorganisms or plants to degrade dyes. These methods are environmentally friendly and cost effective, but may require long retention times and can be affected by variation in pH and temperature. Physical treatment. Physical methods like adsorption, coagulation, flocculation and membrane filtration are effective in removing dyes from wastewater. Adsorption using activated carbon or other adsorbents can efficiently capture dyes, while membrane filtration techniques like reverse osmosis can separate dyes from water. However, these methods may generate secondary waste and require energy intensive operations. So, we know that biological treatments are very much affected by pH and temperature. Similarly, physical treatments are governed by the energy consumption. Chemical treatment. Chemical processes such as oxidation, ozonation and advanced oxidation processes AOPs involve the use of chemicals or reactive species to degrade dyes. AOPs include methods like Fenton's reagent and photocatalysis and can effectively degrade a wide range of dyes, but may be expensive and produce hazardous byproducts. Electrochemical treatment. Electrochemical methods like electrocoagulation and electrooxidation utilize electricity to remove dyes from wastewater, and this we have covered in last few lectures. These processes offer high efficiency and can treat a variety of pollutants, but may require skilled operation and maintenance. It is not very easy that anybody can run an electrocoagulation or an electrooxidation system. So, skilled manpower to operate and maintain are required. Membrane technologies. Advanced membrane technologies such as nanofiltration and ultrafiltration offer selective separation of dyes from effluents based on molecular size and charge. These methods are efficient and require less space compared to conventional treatment system but may be sensitive to fouling and require frequent cleaning. It is not maybe, they get fouled, and membrane fouling is a serious issue, because then the membrane will not let any water permeate through it. So, membrane cleaning maintenance is a big problem. Moving on, let us see what are the green technologies and green nanochemistry based treatment. So, current treatment technologies with a proposed alternative. One promising alternative is the utilization of green nanochemistry for dye remediation. This also we have covered in one of the lectures when we were talking about sustainable and green approaches. This is just a consolidation. Now we are coming to an end of the lecture series. We are trying to compile all that we have learned so far. And since dye is a big problem in the textile effluent, most of the focus of dye remediation is what we have been talking about. This involves the synthesis of environmentally friendly nanoparticles and nanocomposites derived from natural sources like plant extracts or biopolymers. These nanoparticles can efficiently absorb or degrade dyes through various mechanisms such as surface interaction or photocatalysis, while minimizing the environmental impact. So, the focus is on how to minimize the environmental impact of the organic dyes that are present in the textile effluent. Additionally, the use of renewable resources for nanoparticle synthesis reduces the reliance on chemical precursors and minimizes the generation of secondary waste. Green nanochemistry based treatment holds potential for cost effective and sustainable remediation of dye containing textile effluents. However, further research is needed to optimize the synthesis process, enhance the efficiency and scale up the technology for industrial application. And as what I told a while ago, that every technology that is developed in the laboratory needs to be scaled up, needs to be practiced several times before it can be recommended for large scale operations. Moving on, then green nanochemistry based treatment of textile effluent. When it involves utilizing nanoparticles or nanocomposites derived from environmentally friendly sources to remediate dye pollution in wastewater. And here is how it can be implemented. Nanoparticle synthesis. The first step is that we have to make nanoparticles of the chosen material in an appropriate size. Nanoparticles can be synthesized using green chemistry principles, employing natural compounds such as plant extracts, biopolymers or other renewable sources as reducing and stabilizing agents. For example, silver nanoparticles can be synthesized using plant extract like green tea or neem leaf extract, while iron nanoparticles can be derived from plant based materials like rice husk or sawdust. And we ourselves have made silver nanoparticle using lemon leaves, and it worked out very easily. Adsorption. Green nanoparticles possess high surface area and reactivity, making them effective adsorbent for dye molecules in wastewater. The nanoparticles can be dispersed directly into the textile effluent, where they adsorb dye molecules through physical or chemical interactions. This process effectively removes dyes from the water without generating secondary waste. So, adsorption is the phenomena even in this case. Remember, we had talked in detail about the adsorption phenomena of activated carbon. Then we talked about CBBA, that is the coal bottom ash, and now we are talking about the adsorption phenomena that is carried out in nanoparticles. Photocatalysis. Some green nanoparticles exhibit photocatalytic properties, meaning they can degrade dye molecules under sunlight or even under artificial light irradiation. For instance, titanium dioxide nanoparticles synthesized from plant extract can act as photocatalysts to break down dye molecules to harmless byproducts such as water and carbon dioxide. This process offers a sustainable approach to dye degradation without the need of additional chemical inputs. Biodegradability. Green nanoparticles are often biocompatible and biodegradable, reducing their environmental impact compared to traditional metal or synthetic nanoparticles. After treatment, the residual nanoparticles can undergo natural degradation processes in the environment, minimizing long-term pollution concern. So, they are also capable of biodegradation, and this biodegradation definitely then reduces their environmental impact as compared to the traditional metal or synthetic nanoparticles. Scale up and integration. Research efforts are needed to scale up the synthesis of green nanoparticles from industrial applications and integrate them into existing wastewater treatment system in textile factories. This may involve optimizing synthesis parameters, ensuring nanoparticle stability and performance in complex wastewater matrices, and evaluating the economic feasibility of large scale implementation. So, can it be scaled up and can it be integrated with different processes? Research efforts are being carried out to see whether or not it is able to be synthesized in an optimal manner, synthesis parameters are congenial or not, ensuring nanoparticle stability, they should not agglomerate, and performance in complex wastewater matrices. What is their performance in a complex, because it is not just having dye, it is having other organic pollutants, and some of them are very tough to degrade. Regulatory compliance. As with any wastewater treatment technology, regulatory compliance is essential, and we have been talking about it time and again to ensure that the treated effluent meets environmental quality standards. Therefore, it is important to conduct thorough assessment of the efficacy, safety and environmental impact of green nanochemistry based treatment processes before widespread adoption. So, it is very much possible if all the regulatory norms are abided by, but we cannot overlook, because nanoparticles are even more sensitive when it comes to regulatory norms. By harnessing the principles of green chemistry and nanotechnology, green nanochemistry based treatment offers a promising approach to address the environmental challenges associated with dye pollution in textile effluent, and this we have understood very well now, contributing to sustainable water management practices in the textile industry. What are the benefits of green nanochemistry based treatment of textile effluent? As we know that when a technology is brought into limelight, all the benefits are highlighted. But when it is being practiced, it is then that the drawbacks or the challenges are witnessed. So, same way, there was apparent benefit, and therefore, green nanoparticles were used or are being used for the remediation of removal of color from the wastewater. The green nanochemistry based treatment of textile effluent offers several significant benefits. Environmental sustainability over and above, because by utilizing natural compounds and renewable resources for nanoparticle synthesis, green nanochemistry based treatment reduces reliance on chemical precursor derived from non-renewable sources. First and the foremost thing, that it can be regenerated and it is not dependent on renewable sources. This approach minimizes the environmental footprint associated with traditional treating methods and contributes to sustainable water management practices. So, environmental sustainability is of prime importance, and after you have learned the entire course, you should go back with a feeling that environmental sustainability or sustainable practices which can lower the environmental impact is of prime importance. Reduced chemical usage. Green nanoparticles synthesized from plant extracts or biopolymers often require fewer chemical additives or overall chemical load in the treatment process and minimizes the generation of hazardous byproducts, leading to a more environmentally friendly remediation approach. So, it is definitely the word green nanochemistry based treatment itself makes us understand that it is environmentally friendly process of remediation. Energy efficiency. Some green nanoparticles possess intrinsic properties such as photocatalytic activity, which allows for the degradation of dye molecules under ambient temperature and conditions and natural sunlight. So, it does not require any excessive heating or cooling, and natural sunlight can photolyze. This eliminates the need for energy intensive processes such as heating or artificial light irradiation, contributing to overall energy saving in the treatment process. Remember, we were talking about two more things apart from water saving: energy saving and cost saving. So, here it is energy saving as well as cost saving, because no external heating or artificial light irradiation is required. Sunlight, which is ample, can be used. Biodegradability and biocompatibility. Green nanoparticles are typically biodegradable and biocompatible, meaning they can undergo natural degradation processes in the environment without causing harm to ecosystems or human health. After treatment, residual nanoparticles pose minimal long-term environmental risk compared to non-biodegradable alternatives. So, definitely, as they are green nanoparticles, they are biodegradable and biocompatible with the nature. Cost effectiveness. Green nanoparticles or nanochemistry based treatment system can offer cost effective solutions for textile effluent remediation, particularly in regions where access to conventional treatment technologies or chemical inputs may be limited or expensive. Utilizing readily available natural resources for nanoparticle synthesis can help reduce production costs and make the technology more accessible to a wider range of industries. So, it is very cost effective because the total cost involved is for textile effluent remediation comes out to be much less than the traditional or conventional technologies. Selective and efficient removal. Green nanoparticles often exhibit high surface area to volume ratios and specific surface properties, allowing for efficient adsorption and degradation of dye molecules in wastewater. This selective removal ensures effective treatment of textile effluent while minimizing the impact of non-target compounds or beneficial microorganisms in the environment. So, what it means that the entire process is very selective, and because it is selective, it is very efficient, because it is just targeting the dye molecule. It is not a universal kind of system where it is attacking POPs and dyes and heavy metals and surfactants and emulsifiers and so on. It is only targeting selectively the dyes and removal of the dye either by adsorption or by degradation. Compliance with regulation. Adopting green nanochemistry based treatment aligns with increasingly stringent environmental regulations and sustainability goals set forth by governments, industries and international organizations. By meeting or exceeding regulatory requirements for water quality and pollutant discharge, companies can enhance their environmental stewardship and social responsibility. So, any company which is following these norms is considered to be a good company, a voucher of being environmentally conscious. Overall, the adoption of green nanochemistry based treatment offers a holistic approach to addressing the environmental challenges associated with textile effluent. And by now we have understood that textile effluent is a place of too many problems in one box kind of a situation. Promoting sustainable practices within the textile industry and safeguarding water resource for future generation is the need of the hour. However, as I said, when some new technology is brought, the benefits are highlighted, and then the drawbacks are then witnessed when it is practiced from laboratory to large scale experimentation. Some hindrances are faced, some challenges are faced. So, what are the drawbacks of green nanochemistry based treatment? Let us look into that. While green nanochemistry based treatment of textile effluent offers promising benefits, it also has some drawbacks and challenges. Synthesis optimization. The synthesis of green nanoparticles may require a lot of optimization of various parameters such as temperature, pH and reaction time to achieve the desired properties and performance and size of the nanoparticle. This optimization process can be time consuming and may involve trial and error experimentation. So, several experiments have to be carried out with several dilutions at different temperatures, at different pH, each time changing only one parameter to find out which is that optimum parameter at which maximum nanoparticles can be synthesized. Scale up challenges. scaling up the synthesis of green nanoparticles for industrial applications can be challenging. This transition from laboratory scale synthesis to large scale production may encounter difficulties related to reproducibility, cost effectiveness, and maintaining product quality and consistency. So, just a while ago I was telling that anything that works excellently at laboratory level need not necessarily be as efficient in large scale application, and therefore further optimization has to be done. And there are many difficulties that are encountered when it is being scaled up. So, it is all related to how reproducible the results can be at larger scale, what is the cost effectiveness, and how do we maintain the product quality when bulk production of nanoparticles have to be done for large scale experimentation. Nanoparticle stability. Now, this is also a very major issue because nanoparticles tend to agglomerate. If left alone, if there is no destabilizing agent added, they will all come together and become a macromolecule. So, green nanoparticles synthesized from natural sources may exhibit low stability compared to their synthetic counterparts. Factors such as aggregation, degradation, or susceptibility to environmental conditions like pH temperature can affect nanoparticle performance and longevity in wastewater treatment system. Now, as you may recall that wastewater has variable pH, has variable temperature at different stages. Now, if a nanoparticle is added, it may be stable at ordinary condition, but in the new condition, because of the variation of temperature and pH, it may agglomerate. Efficiency and effectiveness. The efficiency and effectiveness of green nanochemistry based treatment method may vary depending on factors such as type and concentration of dyes present in the effluent, as well as the characteristics of nanoparticles used, that is size, surface chemistry, etc. Optimization of treatment conditions and selection of appropriate nanoparticle formulations are crucial for ensuring optimal performance. So, one can see that all these optimization processes are very important in terms of getting effective results and getting efficient results. So, optimization then becomes a very crucial parameter, because unless and until we have optimal parameter, we will not know whether it will give this much of yield every time. Regulatory consideration. Despite their green and sustainable attributes, green nanoparticle may still be subject to regulatory scrutiny regarding their safety, environmental impact, and potential risk to human health. Undoubtedly, any particle which is of nano size can pose a health risk to human. Compliance with regulatory requirements and standards for nanoparticle based technologies may necessitate thorough risk assessment and toxicological studies. So, considering the regulatory consideration, it is very important to make a toxicological study and see whether it poses any risk by assessment of risk assessment. Cost consideration. While green nanochemistry based treatment offers potential cost saving compared to conventional treatment methods, there may be still some associated cost with nanoparticle synthesis, characterization and implementation. It is not free of cost. It is not like CBBA, which was just found as a waste which could be used directly. without much of purification, and so proper nanoparticle synthesis have to be carried out. For that nanoparticle synthesis, cost will be implemented. Then it should be characterized. What is the size of the nanoparticle? So SEM, TEM, AFM, all these technologies have to be adopted for analytical tool to analyze the size of the nanoparticle, and then its implementation. The economic feasibility of adopting green nanochemistry based treatment must be carefully evaluated, taking into account factors such as material cost, labor, energy consumption and maintenance. Public perception and acceptance. Now that is a very important thing which we tend to ignore. We think that nano is safe, and not everybody thinks that way. So there are mental blocks about nanoparticles. Public perception and acceptance of nanoparticle based technologies, particularly those involving novel or unconventional material, can influence the adoption and implementation of green nanochemistry based treatment in the textile industry. So it is not as simple as that. People have a mindset or a pre-notion that anything which is nano can be dangerous. Transparency, communication and stakeholder engagement are essential for addressing concerns related to safety, environmental impact and sustainability. Addressing these drawbacks and challenges requires interdisciplinary collaboration among scientists, engineers, regulators, industry stakeholders and policymakers to advance research and development and implementation of green nanochemistry based treatment approaches for textile effluent remediation. So if a scientist says that it is safe, it is not all. The engineers who are involved in making the wastewater system design, the regulatory body, the industry stakeholders all have to understand the seriousness of green nanoparticle remediation technique, and all the assessment, risk assessment, ecotoxicity, all have to be assessed beforehand before it can be actually implemented on large scale. See, when it is done in a laboratory, very small amounts of nanoparticles are actually used, but in a bulk, in a mill where there is lot of wastewater in gallons and gallons, 1000 cubic meter, it is a huge amount of water, wastewater. When that has to be treated with this technology, imagine the kind of magnitude that the nanoparticles would be required, and they should work as efficiently as what they have worked in the laboratory, and then only that practice will be considered as a safe practice. So, green chemistry offers several promising approaches for remediation of textile effluent, addressing both environmental concern and the sustainability of textile industry. And here are some strategies. Biodegradable surfactants. Traditional surfactants used in the textile processing can be replaced with biodegradable alternatives. Wherever possible, switching over to biodegradable chemicals is always a safer option. These surfactants break down into harmless substances, reducing the environmental impact of the effluent discharge. Enzymatic treatment. Enzymes can be employed to degrade dyes and other organic compounds present in the textile effluent. Enzymatic processes are often more specific and efficient compared to conventional chemical treatment and they produce fewer harmful byproducts. So, what it means, wherever possible, enzymes should be employed because they can degrade the dyes and other organic compounds, yet they are not chemical intensive. That means they can biodegrade and will not cause any extra pollution. Adsorption using bio-based material. Bio-based adsorbent such as activated carbon derived from agricultural waste or biochar can effectively remove dyes and other pollutants from the textile effluents. These materials offer a sustainable alternative to conventional adsorbents and can be generated or regenerated for multiple uses. So, if any material can be reused and regenerated, definitely it cuts down the cost. Also, its effectivity should not be jeopardized. That means every time the adsorption efficiency should be the same even when it is regenerated. Membrane filtration. Membrane technologies such as ultrafiltration, microfiltration, nanofiltration and reverse osmosis can separate contaminants from textile effluent based on size and charge, and this we have understood very clearly. Green alternatives include biopolymer membranes derived from renewable resources which offer comparable performance to synthetic membranes with lower environmental impact. So, now people are moving even in membrane technology from synthetic membranes to biosynthesized membranes, where the precursor of the membrane is from biological source, and they have found that it is very useful. Ozonation and advanced oxidation processes, AOPs. Ozonation and AOPs involve the use of ozone and other oxidizing agent to degrade organic pollutants in water. These processes can effectively break down dyes and other recalcitrant compounds present in the textile effluent, leading to cleaner discharge. So, the whole idea is that how do we make the waste water which is loaded with pollutants to become at least such that it can be discharged safely into the water bodies. And for that, the AOP methods, that is the advanced oxidation processes, have been found to be very conducive. Why? Because ozone or use of hydrogen peroxide and UV irradiation and these penton reactions are all very safe methods. Water recycling and closed loop system. Implementing water recycling and closed loop system within textile manufacturing facilities can significantly reduce water consumption and effluent discharge. By treating and reusing process water, these systems minimize the environmental footprint of textile production and they minimize the use of fresh water consumption. So, a lot of emphasis is also being given that during the remediation process, somehow the water should be purified to such an extent by some kind of closed loop system that it can be reused without further purification or any kind of extraction. Green solvents. Solvent based processes in textile manufacturing can be replaced with greener alternative such as supercritical carbon dioxide or bio-based solvents derived from renewable resources. Now, this is one new aspect. These solvents offer similar performance while reducing toxicity and environmental persistence. So, green solvent is again a relatively new concept where a lot of solvents which are either chlorinated solvents or hydrocarbon solvents are being replaced by these bio-based and renewable derived from renewable resources, and these solvents have been found to be very useful as they have less of toxicity. Life cycle assessment LCA. Conducting life cycle assessment can help identify areas for improvement in textile production processes, including effluent treatment. By considering the environmental impact of each stage from raw material extraction to end of life disposal, manufacturers can optimize their operations for sustainability. So, LCA is one last objective that helps to identify whether or not to proceed with these new technologies, because we have to still assess how is it going to be performing in the long run. Maybe an immediate short term effect is very bright, but the long term effect or the persistent in the environment can pose serious problems. So, by doing life cycle assessment, it is possible to assess how it is going to behave in the long term. Implementing these green chemistry based approaches requires collaboration between researchers, industry stakeholders and policy makers to develop and adopt sustainable solutions for textile effluent remediation. It is not just one person's job. It is not the job of researcher that I have done research and that is it. It should be validated by the regulatory bodies. It should be accepted by the policy makers, and it should be adapted by the mill owners. Benefits of green chemistry based remediation textile. Green chemistry based remediation of textile effluent offers numerous benefits, both environmental and economic, and here are some of them which are listed. Reduce environmental impact. Now, everywhere, wherever we are proceeding, wherever we are discussing in detail, this fact that environmental impact has to be reduced somehow, and that can be achieved using green chemistry techniques focusing on minimizing or eliminating hazardous substances in chemical processes. By adopting these methods for remediating textile effluent, the release of harmful pollutants into the environment is significantly reduced, leading to cleaner water bodies and healthier ecosystems. Resource efficiency. Green chemistry emphasizes the efficient use of resources such as water, energy and raw materials. Remediation processes designed with green chemistry principle in mind often result in reduced resource consumption, contributing to sustainability in textile industries. So, how can we say that this is an efficient resource? So, because it is from the green chemistry, it does not automatically become a resource which is efficient. We have to see the remediation processes, how it is working, and then only we can come to a conclusion that yes, it is safe. Therefore, remediation processes designed with green chemistry principle in mind often result in reduced resource consumption, contributing to sustainability in the textile industry, but it is not automatically. It is assumed that it will be consuming resource which will be less. Non-toxic solution. Traditional remediation methods may involve the use of toxic chemicals, which can pose risk to human health and the environment. Now, green chemistry based approaches prioritize the use of non-toxic and less toxic alternatives, ensuring that remediation activities do not introduce additional harm. So, mostly they are non-toxic, and that is why they have been recommended. It is no point in using a toxic substance for remediation of another toxin. It does not make any sense. Cost saving. While there may be initial investment required to implement green chemistry techniques, in the long run they often lead to cost saving. These savings can result from reduced waste disposal cost, lower energy consumption and decreased reliance on expensive chemicals. So, any new technology requires new infrastructure. For erecting the new infrastructure, there will be some initial cost, but in the long run there is an eventual saving, and the savings come from reduced waste disposal cost, because disposal of sludge itself is a big cost effective issue. Lowering energy consumption, and because they do not require too much of energy, obviously if they are practiced, that is the green chemistry based remediation methods, they will use less energy and it will be consuming less of expensive chemicals. Compliance with regulation. Many countries have strict regulations governing the discharge of industrial effluent into water bodies. Green chemistry based remediation methods help textile manufacturers to meet these regulatory requirements by offering cleaner and more sustainable solution treating effluent. So, it is also very close to the regulatory norms, abiding by them. Enhanced corporate image. Now, all those companies who are practicing the green chemistry are using this as their advertisement for their products, and consumer is also getting affected by this, that they are using sustainable methods. So, it enhances the corporate image. Adopting environmental friendly practices including green chemistry based remediation can enhance a company's reputation and appeal to environmentally conscious consumers. This positive image can lead to increased brand loyalty and market competitiveness. Innovative and research opportunities. Embracing green chemistry encourages innovation and drives research into alternative sustainable technologies. This can lead to the development of new, more effective remediation techniques and provide opportunities for collaboration between industry, academia and government agencies. So, there is always a scope for new research, and new research and innovation can only happen when industry, academia and government agencies come together to find newer solutions. Long-term sustainability. By addressing environmental challenges associated with textile effluent, green chemistry based remediation contributes to the long-term sustainability of textile industry. It helps ensure that future generations can continue to enjoy the benefits of textile without compromising the health of the planet. Overall, the adoption of green chemistry principle in the remediation of textile effluent offers a holistic approach to environmental protection, resource conservation and sustainable development. But there are drawbacks of green chemistry based remediation as well, although there are many benefits. But let us now look at the drawbacks, because every technology has two sides of the coin. One is the benefit and the other side is the drawback. While green chemistry based remediation of textile effluent offers numerous benefits, there are some potential drawbacks or challenges which need to be considered. Cost consideration. Implementation or implementing green chemistry techniques may initially require investment in research, development and infrastructure, depending on the scale of the operation and the availability of the resource. These upfront costs could be perceived as a barrier, especially for small companies or those operating on light budget. So, for a small company to make big investment is a little difficult situation, and therefore, companies that are working on light budget or have a very small business model cannot afford to invest too much in the infrastructure. And as I told you in the beginning or a while ago, that some infrastructural investments have to be done for most of the new technologies. They cannot be run on the existing traditional infrastructure. So, technological limitations are there. Some green chemistry methods may still be in the early stages of development or may not yet be commercially viable at scale. This could limit the range of options available for remediation, particularly in complex cases where multiple pollutants need to be addressed simultaneously. So, the matrix of the wastewater and the type of technology that is being developed may or may not match. So, that becomes a real technological limitation, and therefore, a lot of experimentation has to be done to actually finalize that this is working and this is not working. Effectiveness and efficiency. While green chemistry approaches aim to be environmentally friendly, as the name suggests, they must also be effective at remediating textile effluent to acceptable limits. So, just by saying that this is a green chemistry approach, it does not mean that it will effectively remediate the wastewater. So, it has to bring down the pollution level up to acceptable level which has been stipulated by the Pollution Control Board. Ensuring both effectiveness and efficiency without compromising environmental goals can be a challenge and may require ongoing optimization and innovation. Complexity of effluent composition. Now, this we have talked time and again, because the production throughout the day is not of one type. There could be different types of production happening one after the other, and in the day the effluent composition may not remain the same all the time. So, there is a complexity that is there in the effluent composition. Textile effluent can be highly variable in composition, containing a wide range of pollutants such as dyes, heavy metals and organic compounds. Developing green chemistry based solution that can be effectively treated this complex mixture of contaminants may be technically challenging and require tailored approaches for different types of effluent. So, that is why I said in the very beginning that knowing the composition of the textile effluent at the onset is very important to strategize which technology will work, to what extent, what are the pollutants that are mainly present, and that is where the analysis of the effluent plays a big role. Regulatory compliance. While green chemistry techniques aim to reduce environmental impact, they must still meet regulatory standards for effluent discharge, ensuring compliance with these regulations while implementing innovative green chemistry solutions. Scale up challenges. Transitioning from laboratory scale experiment to industrial scale implementation can present challenges in terms of scalability, reliability, cost effectiveness. Green chemistry based remediation processes may need to be adapted and optimized for larger scale operations, which can involve additional time and resource. Limited awareness and education. Because it is a new set of chemistry, awareness and understanding of green chemistry principles and technologies may be limited within the textile industry and even among regulatory agencies. People are still learning, in the process of learning. Overcoming this barrier may require investment in education, training and outreach efforts to promote the adoption of green chemistry practices. Risk of unintended consequences. Introducing new chemicals and processes, even those deemed environmentally friendly, carry a risk of unintended consequences. We still do not know what is their long term effectivity. This could include the formation of harmful byproducts, impact on ecosystem dynamics or unforeseen environmental risk that may emerge over time. Addressing these challenges require collaboration between industry stakeholders, researchers, policymakers and regulatory agencies to promote innovation, overcome barriers and ensure continued advancement of green chemistry based remediation solutions for textile effluent. So, best modern practices in sustainable remediation processes, let us now compile everything. Advanced oxidation processes is one, biological treatment is second one, membrane technology is third one, adoption of techniques is fourth one, recovery and resources of the resources is also of prime importance, and process optimization and automation of course is one of the most important set of parameter that needs to be really practiced very hard. Employ advanced monitoring and controlling system to optimize remediation processes. So, life cycle assessment of new material, collaborative approach which we have already discussed are some of the best modern practices in sustainable process of textile effluent. To summarize, in conclusion, the adoption of modern practices in effluent remediation represent a significant step forward in addressing the environmental challenges associated with industrial activities, particularly in sector or like textile. By integrating innovative technologies and sustainable principles, stakeholders can achieve effective pollution control while minimizing environmental impact, conserving resources and promoting long-term sustainability. Key solutions or conclusions of the best modern practices are diverse technological approach. The best practices encompass a diverse range of technological approaches, including advanced oxidation processes, biological treatment, membrane technology, adsorption techniques, recovery of resources, process optimization and automation. Each approach offers unique advantage and can be tailored to specific characteristic of the effluent and site condition. So, it is not one method, it is a collaborative method where all the advanced oxidation processes or biological treatment, membrane filtrations have to be considered. Integration of green chemistry principle. Sustainable remediation processes prioritize the principle of green chemistry, emphasizing the use of non-toxic and less toxic alternative, resource efficiency and pollution prevention. So, by minimizing the generation of hazardous substance and reducing the reliance on conventional chemicals treatment, green chemistry based approaches offer safer and more environmentally friendly solutions. So, holistic and collaborative approach is required. Continuous improvement and innovation are focused. And so, to conclude, we can say balancing environmental, economic and social consideration is of prime importance. Sustainable effluent remediation involves balancing environmental, economic and social consideration to ensure that remediation efforts are not only technically feasible and environmentally sound, but also economically viable and socially acceptable. By considering the triple bottom line of sustainability, stakeholders can achieve more holistic and equitable outcome. In conclusion, the adoption of modern practices in effluent remediation represents a proactive approach to addressing environmental challenges, promoting responsible industrial practices and safeguarding the health of ecosystems and communities. By embracing innovation, collaboration and sustainability, stakeholders can work together a future where industrial activities coexist harmoniously with the natural environment. That means that the prime aim of using any or every technology is to somehow not let the environment get polluted. If the environment is not polluted, if the water bodies are not polluted, then the aqueous ecosystem and the land animals and plants can all survive in a very happy manner and in a very healthy manner. So, what it boils down to, whichever technology we adapt, it has to somehow reduce the pollution load, whether we are using green chemistry approach or we are using traditional methods or technologies, or whether we are using some of the emerging technologies. The prime importance lies in the fact that it should be safe. So, with this we have come to an end of this lecture, and I am sure there have been many takeaways from this lecture about the green chemistry approach and the greener technologies, although they are still under the experimental stage, but they appear to be very promising for future. So, with this we end this lecture. Thank you.